For our next problem, let's see if we can compute the work required to pump all of the water out of a tank that has the shape of a sphere. So let's think about a spherical tank. So let me put a little dot here so I know where the center is. Something like this. And let's draw some lines like that. Okay, so and then this is just a vertical cross section, so it's actually a sphere. So it's actually the shape of, you know, a nice sphere like this. So the slices for these work problems are always horizontal slices because each horizontal slice is lifted by a different vertical distance to get gravity. And so the slices here, if we imagine the cross sections, they're going to have the shape of circles. So we have these little circular cross sections. So if you take a sphere and just slice it like this, you're going to get a circle out. And that slice is going to look something like this. So for the problems that are spheres or cylinders, like horizontal cylinders, the way to do this is to look at the best way is to let x equals 0 be at the center. So these elevation x equals 0 is at the center of the sphere. Let's say it's a sphere of radius r, so we have x is equal to r is at the bottom, and x is equal to minus r at the top. So the sphere will range from x is equal to minus r to plus r, which will give us the limits of integration when we do that. And so basically, the position of the sphere is x, and the reason for setting x equals 0 at the center is so that this length has, this is a length either plus x or minus x. Now we want to know the length across the bottom. So with a cylinder, you find the total length across. With a sphere, we just want the length from here to the edge because that's basically the radius of that horizontal circular slice. So the trick is that if we connect the center of the sphere to the edge, well, that has to equal the radius of the sphere, right? Because if you're going from the center of the sphere to the surface of the sphere, that's just going to be the radius regardless of where on the surface you're going to. So using a right triangle, we see that this little segment has length square root of r squared minus x squared. So this little circular slice at that elevation is a circle with radius square root of r squared minus x squared. So the area as a function of x is going to be pi times this quantity squared. So it's pi times r squared minus x squared. Now you can check if you integrate from minus r to r of pi r squared minus x squared dx, you should get 4/3 pi r cubed. So that kind of confirms the way we set it up because that recovers the total volume of the sphere. So if you work this integral out, which I encourage you to do, you can pause the video and work it out on your own, you should get 4/3 pi r cubed. So the volume, the little volume of the slice is going to be pi r squared minus x squared delta x. The mass of the slice is therefore rho times delta v, so that's the mass. The weight of the slice, which gives us our force, is just rho g delta v. And the total work on the slice, we multiply the weight by the distance. So let's say that we're actually pumping this water to the very top, or a distance of d above the top. So we're not just pumping it to the top of the tank, we're pumping it to the top of the tank and up to a spout that's a height d above the top of the tank. Well, this length is rho and this is d. So to get from the center of the tank to the height at which we're pumping it, it's going to be r plus d. But we're starting down here, so this length is x, so the distance is r plus d plus x. So the work is r plus d plus x times rho g delta v. Now notice that this works regardless of x is positive or negative. The way I have this with x pointing down, this would be a positive x value below the center, so I'm adding the x value to r plus d. If I'm up here, I already have a negative x value, so it's r plus d plus x. X is a negative number, and it will be less than r plus d. So r plus d plus x always works. If the x-axis was pointing up instead of down, it would need to be r plus d minus x. So be very careful. It depends on how you set up your coordinates. Since x is pointing down in this case, the distance that I'm moving will be r plus d plus x. And then when we integrate this, we get the total work. So the work is equal to an integral of r plus d plus x, rho g I'm just going to pull out, and the delta v, we get a pi, and then times r squared minus x squared dx, as x goes from minus r to plus r. So this is the integral we need to work with. Now I'm going to expand the integrand as r plus d times r squared minus x squared plus x times r squared minus x squared. So basically I'm going to treat this as one piece and then this x, and then factor this r squared minus x squared in. So basically the work is rho g pi times an integral of r plus d, which is also a constant, I could pull that one out, r squared minus x squared, and then plus rho g pi integral of x times r squared minus x squared. Now this second integral is 0 because r squared minus x squared is an even function. When I multiply that by x, the whole thing becomes an odd function, and when I integrate an odd function from minus r to plus r, I just get 0. So that second integral is 0. So we just have rho g pi r plus d times the integral from minus r to plus r of r squared minus x squared dx like this. So that's equal to the total work. Now if you work this out, work it out, I know, what you get is you get rho g pi r plus d, and this integral gets you 4/3 r cubed. So this integral works out to be 4/3 r cubed, and again you can pause the video and confirm that. Now what do we have here? So something very interesting is happening. We have 4/3 pi r cubed. I'm rearranging the terms. This is just the total volume of water. Multiply it by rho, that's the total mass of water. Multiply it by g, that's the total weight of all of the water in the tank. So if we just take the total weight of all the water in the tank and multiply it by r plus d, which is the distance traveled by the center of mass. So the center of mass is right in the center of this, and the center of mass is traveling through a distance of r plus d. We again see that the total work is equal to the total weight of all of the water times the distance traveled by the center of mass. Essentially, why this happens is if we think about the slices in pairs, like we have a slice up there and an opposite slice down here. This one's traveling r plus d minus x, and this one's traveling r plus d plus x. So you get like one's a little bit above r plus d, the other one's a little bit low. So the difference between those two slices r plus d cancels out. So knowing how to set this up is still important, because what happens if you have a hemispherical bowl and you want to pump all the water out of the hemispherical bowl? Okay, well, because there's no symmetry anymore, unless you actually do another integral, you don't know where the center of mass is. So you do have to set these up and know how to do the integrals. But it is very reassuring to see that when we set this integral up, we get exactly what we would expect.